Welcome back to ECE 320A. Oh, what I forgot to put on here is your passport. Your passport is due on Sunday. If you haven't turned in your passport assignment, it's due into the assignment drop box on Sunday evening. The next due date for you is then homework number 1, so you don't even see the passport listed here, but maybe I should add that here if I can even do it. Passport is due on Sunday the 20th. You don't have to attend classes the following day, so you can really hit it hard Sunday night. You can really work on that passport and then submit it before 11:59, which is when it's due. Homework number 1 is due in 29th, which is I think a week from Tuesday, the upcoming Tuesday. You need to continue working studying chapter 10. Exam number 1 is on Thursday, the 14th of February. And exam number 1 material has now been opened up, I think. And you should be seeing many practice exams, previous exams. There are a lot, and if you can work those forwards and backwards, you should be set for the exam number 1, which occurs on the 14th of February. And there's 2 different exam types on the practice material. One is a blank exam, which is what you will receive, and the other one has many different solutions available to you. But I would strongly encourage you to look at the non-completed exam first to get your brain thinking, how would I approach this problem? Can I do this problem? Oh, I can't. Now what do I do? Well, struggle with it for a while, and then as a last resort, look at the solutions, because you want to be fully prepared for the exam on the 14th. And you'll be given a blank, well, it'll have problem statements on it, but that's it. No worked solutions. On the syllabus, for whatever reason, I had you going to another room, but now I've corrected that. So if you see the syllabus has been updated to maybe Tuesday's date. What is today? Thursday? Maybe I updated it on Tuesday or Monday sometime. Hopefully it's now displaying the correct office, which is on the 5th floor of the ECE building, room 23 on the 5th floor. That's where I'm holding my office hours, and there's 4 different days of office hour times, an hour each of those 4 days. Friday, no, I don't have office hours scheduled. If you can't make those, let me know and we can maybe work something out. Today what I want to talk about is the complex power triangle. I may not get this colorful again, but here you can hopefully color code the real power, P, the imaginary or the complex power, Q, and their sum, vector sum. Vectors, don't treat them like just everything in the same direction. Now you have to worry about length and angle when you're adding up powers. You can't just add up powers unless you add them up component-wise. You can add up all the P's, you can add up all the Q's, and then you say P total plus JQ total gives me S total. But you can't just say magnitude of S1 plus magnitude of S2. I hope you understand that. If you don't, draw a couple of vectors from head to tail, or however you want to describe it, and put them at weird angles, and you can hopefully see that the 2 lengths may not be equal to their vector sum. That's important to understand. We'll look at a complex power example relative to the source, load, and line. Then we will look at complex power of a 2-terminal element. We'll develop many different ways of expressing complex power in terms of voltage and current, impedance and voltage, etc. You can have a lot of different ways of writing complex power. and then we'll start talking about what I just talked about, which is multiple loads, where you have to add them up vectorially or component-wise, your loads. Keep track of your P's, keep track of your Q's. You can combine those, but everything needs to be in a vector in terms of adding S1 to S2, etc. I did this beforehand so that I could make it pretty. The complex power triangle. P is the real power, that's horizontal. Q, what's Q correspond to? Reactive, but what's that mean? It's the sign, it's the imaginary. Come here, where is it? Where is it? It's imaginary, but it's really sort of this power that gets stored and then returned, stored and returned in these energy storage devices, or these elements in your power system, these inductive elements and these capacitive elements. If you had a lot of inductors in your industrial plant, you actually might want to install a bank of capacitors to try to counteract all of that inductive behavior. You really want that Q to be as small as possible, because the power company is going to charge you based on the length of S, and if S is much longer than P, you're being overcharged for the power that you can physically use. P is the power you're using. Q is sort of due to these reactive elements in your system, which are there because if you have a bunch of machines, you have a lot of inductive coils in these machines to make them work the way you want. But that's storing and releasing a lot of energy. That makes S much longer than P. If Q gets down to 0, can you see that S is equal to P? And what's the angle when S is equal to P? 0. And one of the pieces, this cosine of theta, if I scroll it up just a little bit, that's our power factor, and the power company is very interested in that power factor. If it gets small or much different from 1, then they may charge you a surcharge or a premium for the power that you're actually able to use. So you're wanting, ideally, that theta to be as close to 0 as possible. And I think then if you view that in terms of this triangle, you're trying to make Q small. And if Q in this case was inductive, if we put in some capacitors to put in another Q that's negative, do you see how in the vertical direction we could shrink the net Q, which would be the positive piece, together with the negative piece to make the Q smaller? And that's what we might do in a real-world scenario. We may increase the setting on that capacitor bank so that we can reduce Q from that large positive amount. We're trying to make S be closer to P, to make that angle smaller. And P is the real power. That's the power that does work for us. S is the complex power, and that incorporates P and Q. And the power company is concerned with Q because they are going to charge you for S, essentially. The magnitude of S, which is the apparent power. That's the power that apparently you need to drive your plant. And so the power company is going to charge you for that power that you apparently need, and not just what you're using. Just kind of keep that in mind, I hope, as we're talking about this, and you're going to say, what is complex power? Why are we worried about it? Well, it physically means something. P and Q. Even though Q is the imaginary, it's there. It's orthogonal to the P. And so Q, you may not want to worry about it, but really you should. The power company is definitely worrying about it. The reactive factor is important. There's the sign. The S-I-N-E, not S-I-G-N, but you'll probably have a sign on your desk at work saying, get that Q to smaller if Q is big. So then you have to worry about both signs, the S-I-G-N on your desk and the S-I-N-E of that angle. Does anybody remember the first day of class? He gave us a quiz. Did I collect the quiz? You don't remember? I collected everyone else's quiz but yours. And I think everyone got a 100. Congratulations on that quiz, except you. Because you were asleep. I hope you're not offended by me. Okay. Picking on you occasionally. But here's the quiz that we had in day 1, and I wanted you to get going. That's why I called it a quiz. And this should be something that you're familiar with in terms of analyzing now that you've seen it a couple of times. But what we want to do today is actually work through this scenario, and now we might tie it into where we're going in chapter 10, which is we're going to have loads, and we may have a transmission line that feeds that load. That's why I've labeled the top or the horizontal impedances as the line, and the load, and it's hopefully bigger than what we're losing in the transmission line. Hopefully we're delivering more power than we're consuming just to get from the source to the load, and the relative values indicate that. But the load is then the vertical impedance in this picture. And what I want to do now is talk about the complex power associated with the source and the load and maybe the transmission line. And a lot of times in this class, when we say line, you may want to just insert transmission line. That's usually what we're meaning. When I say line, or in the accepted jargon, usually they just say the line impedance. It's really the transmission line impedance, or the impedance of the transmission line. That everyone should have. And now let's see if we can find the complex power of the source. But before we do that, let's just remind ourselves about the passive sign convention. And you shouldn't have to write this down. I just want you to understand it, because you'll have access to these notes. In a minute, we'll slow down, and then you can start putting pen or pencil to paper, right? You can do it now if you want, but I would say listen now and just make sure you understand what we're talking about. When I say the passive sign convention, then we're talking about the absorbed power of that particular element or system. And for the passive sign convention, we want the way that we've labeled the current positive. In this case, it's going from left to right. If it goes into the positive terminal of the system or the element, then that's going to give us a positively absorbed amount of power. If, when we end up with all the calculations, some of those values end up being negative, then we say, oh, we had a negative absorbed power. We've actually supplied that amount of power. Is that clear? So here we just say, let's now, in this case, I would say, oh, my VI star is going to be positive, and then I just worry about the numbers that result after I've computed VI star. And if any of those end up being negative, then in fact, because I had a negative absorbed real or a negative absorbed reactive, I actually was supplying that component instead of absorbing it. Question?
Wasn't it that apparently before mastering they say like delivered, but that's not exactly correct, or
So now you have to be clear maybe on the verbiage. Maybe the question was something about delivered power in mastering. I would say they are probably, and I would have to read the problem, but when they say delivered power, they're probably saying, is it absorbed by, or they may say, how much power is your source delivering? Then I would say, how much is the source supplying to the load? So delivered to the load would be supplying to the load. So if they use that word, I apologize, it's not consistent with what I'm saying. I think it's more informative to say supplied by the source. Is that clear? In this case, this positive sign, which a lot of times we won't even write down, is because our positive current direction was going into the positive voltage terminal of our element before the current went through that particular element or subsystem. And that's the amount of power absorbed by that device or element. That's the passive sign convention. And we want to now find out the power associated with our source. Is it delivered or supplied, or is it absorbed? What's going on? So in this case, we could have really sort of a couple of different ways of viewing it. Suppose we said, what's the complex power absorbed by the source? Using, and so now let me call this S sub S. That's sub S is for the source. The big S is for the complex power, and the bar, I may or may not remember to use it, is because in general S is a complex number. But if I now want to write out how much complex power is absorbed by the source in terms of those two variables that I have indicated here in my diagram, V sub S and I sub S. In terms of V sub S bar and I sub S bar, what's the complex power absorbed by the source? What's the formula that I want to use? Is it clear what I'm asking? So now, is this current I sub S? And what you might want to do is do the following. You might say, well, this is confusing, so let me do this. That's really what I have for V sub S, and now I sub S is right there. Is the positive direction of I sub S going into the positive terminal of the source before it goes through that voltage source? No. So what's my formula or expression for the absorbed complex power by the source? It's a negative, isn't it? This would be a minus. In terms of these complex phasors, V sub S bar, I sub S bar, oh boy, that's complex conjugate, star. That's one way of writing it. Or you could say, what if I said, what's the complex power supplied by the source in terms of the same V sub S and I sub S? Let me call this a different variable. Let me put a party hat on it, hat. And now this is the complex power supplied. The first one was the complex power absorbed. Now we want to know what's the formula if it's supplied in terms of the same V sub s and I sub s. Now the supplied power is if the positive current, the way I've drawn it, is coming out of the positive terminal after passing through the element, then it is a supplied amount of power. So in this case, it would simply be V sub s bar I sub s bar star. So if we wanted to calculate the complex power supplied by the source, we could use the V sub s phasor and the complex conjugate of the I sub s phasor. Do we have both of those quantities? Do we have an expression for I sub s bar? We can find it, but we don't have it yet, do we? So how do we find I sub s bar? We do have V sub s, and now this is in terms of RMS. So how do I find I sub s bar? Ohm's law, KVL, Ohm's law, however you want to state it. We have several impedances, but everything's in series, isn't it? So we can just add up all of those series impedances and use that impedance via Ohm's law, V is equal to ZI, to find I. That means to do this, let's first find the total impedance. We have the impedance associated with the transmission line, Z sub little l, plus the impedance of the load, or that now says our total impedance is 80 plus J60. Or now we can use that to find the current in that series circuit. I sub s bar is just V sub s bar over the total impedance. That's 220 at 0 degrees divided by 80 plus J60. And now you want to start getting comfortable with complex math. Math with complex numbers is what I'm meaning by that. In this case, we have Z sub t. We could view that also as a triangle. We have a real part of 80 and an imaginary part of 60. And here is now our Z total, and there's the angle of that impedance, or the magnitude. Since we are actually forming a product or a division, it's probably easier to talk about our complex numbers in polar form. That's why I'm converting 80 plus J60 that's in rectangular form into polar form, because now it's easier to combine. We just have to divide the magnitudes and subtract the angles. The magnitude of Z sub t is now the square root of the real part squared plus the imaginary part squared. And this is a 3, 4, 5 triangle. So this ends up being a magnitude of 100. The angle, theta sub z, is now the inverse tangent of opposite over adjacent, and that is this familiar angle 36.87 degrees. Now we're in a pretty good position to find I sub s, the current flowing in that series circuit. I sub s is now 220 at 0 degrees divided by 100 at 36.87. Or the current is now 2.2 amps at minus 36.87 degrees, and that's an RMS value. Now we actually have V and I. We can calculate this complex power supplied since I'm hatting it, and that's just V sub S, I sub S conjugate. Am I on the right track?
What's the conjugate of?
Don't you want to conjugate that current? So we need to change the sign of the angle of our current, or I could have erased this and done, oh my. Shouldn't get too aggressive with my eraser, should I? So let's do it the other way. We okay now? I'm not, but now we know how much. If we multiply that out, we need to multiply 220 by 2.2, or we now have 484 at an angle of 36.87 degrees. This is a complex power. That's VA, and what is it? Is it supplied or absorbed? That we said was supplied, didn't we? So you need to keep track of that. And apparently, according to mastering, they may call it delivered. Then I'm not. The question is delivered by or delivered to. I'm received. I mean it. Hopefully you can figure out what it means. Okay. So yeah, if you're wrong, you can flip the sign if you've done your math right. But now we can simply convert this to rectangular form to find the P and the Q. We now just multiply 484 by the cosine of that angle plus J 484 times the sine of that angle, and we end up with 387.2 plus J 290.4 volt amperes. And this is now P sub S. That's now Q sub S. This is in units of watts. This is in units of vars. And the sum, the complex sum, is in volt amperes. Do those numbers seem reasonable? 484, if 36 was instead 45, then the real part and the imaginary part would have been the same. 36 is a little less than 45, so we should have more real part than we have imaginary part. Sort of a way to quick do a gut check on, is this making sense? And relative to each other, they seem to be consistent. Yes? So do we decide, I think in this case, I may have in the quiz, I might have had, 220 times the square root of 2 times cosine of something. In this problem today, I've already converted it to an RMS value or magnitude. But once we've worked or said this is RMS, what we compute, if we're using the Z, the impedance, the current is going to be in an RMS unit. If we needed to convert this back to a time domain waveform, with an amplitude preceding cosine, you would need to scale that V sub S by the square root of 2. Does that answer your question? But here, yes, I basically, today, we started with these in RMS units. Now we can just start drawing triangles, right? If we wanted to understand what we have, we could say, well, what's the complex power triangle associated with the source? And here we could simply say, oh, it was 387. The imaginary component, or the component orthogonal to the real, was 290, and it was actually positive. And then we have this, which had a length of 484, and the angle was 36.87. And now with respect to this picture, what kind of a load was that? Inductive. One, you could say, well, you drew an inductor. Of course it's inductive. But maybe on the exam I might do something weird and draw an inductor and give it a negative J value. What? So but in this case, Q was positive. That means it's inductive, right? The result. So in here, we can say, oh, Q sub S was greater than 0. Our load was inductive. What about now if somebody asks you the complex power of the load? How is that different from what we just computed? So now we have, if somebody wants the complex power of some load or line or any impedance, you need to worry about its voltage and its current. And then you do what? Voltage times its current conjugated. So in that case, we would say, oh, in terms of what we have, if somebody just asked me for the complex power of the load, I might say, well, S sub L, capital L, is plus V sub L, I sub L conjugate. But do we already know any of those pieces? We know the current, don't we? Because this was a series circuit. This, we can say, oh, that's the same as what we've already computed. And then we can say, well, I don't want to compute V sub L directly or explicitly. I know V sub L in terms of the current through that impedance combination. That's just Ohm's law. So now I can say, oh, V sub L, I sub S star is equivalent to Z sub L, I sub S, I sub S star. Are we okay with that? This is simply V sub L. But if you remember how to combine, boy, I need a vacation. If you remember how to combine a complex number times its conjugate, what do you end up with? What is A plus JB times A minus JB? Correct. It's just the magnitude squared. So this is now the magnitude of I sub s squared. Do you see how we've maybe simplified our analysis that's necessary? We had I sub s, which is maybe has a magnitude and an angle. Now we just have to work with the magnitude and square it and multiply it by the load impedance. And then we don't have to do all of this. Oh, let me first calculate V sub L, then let me multiply these two complex numbers together in order to find the complex power. In this case, the complex power absorbed by the load is 78 plus J 59 times the square of 2.2. And if you do that, algebra, you will end up with 377.52 plus J 285.56 volt amperes, where this is now the real power of the load in watts. This is the reactive power in VARs of our load. Question?
Can I, in the power formula, can I put voltage square over C?
So you're getting ahead of me. You're saying what is another formula for the complex power using voltages, and we'll derive that. But it's actually the magnitude of V divided by the complex conjugate of the impedance, and we'll show that in a minute. Here it's easier to remember. It's Z times magnitude of I squared. That one's pretty clean because you can think of IR squared as my power in the real case, but it generalizes to S is equal to Z I magnitude squared. We could now view this. I could say, what's the apparent power of the load? Why are you asking so many powers? You now have the complex power, you have the real power, you have the reactive power. Now you want the apparent power? How would I find the apparent power of the load? It's the length of the complex power, or it's the hypotenuse of a right triangle, isn't it? We're not doing that heavy of lifting in terms of algebra. Just draw a triangle and say, here's the horizontal part, here's the vertical part. Oh, the apparent power is just the hypotenuse of that right triangle, because the P and the Q are always 90 degrees apart. In this case, we would just convert this rectangular form to polar form, if you have a calculator that does that, and you end up with 473.36 at an angle of 37.1 volt amperes. Now, I guess maybe what I should have done was, maybe somebody's questioning, where in the world did this I times its conjugate end up being the magnitude of I squared? Let's just convince ourselves that that's true. Suppose we now say A plus JB times A minus JB. Or really, that's now what I could say is I sub S times its conjugate. And now you use your favorite strategy. Did everybody have aluminum foil when they were taking this? Foil when you were doing quadratics or multiplying first, outer, inner, and last? I never heard that before, but I have heard it now. So now I could do FOIL to expand this product. I could say the first terms, And now I'm not going to worry about it. I'm just going to say this is JBA minus JAB minus J squared B squared. Is that okay? Maybe I should make this a little bit. The JBA minus JAB, A and B commute. Those are just scalars, so that's the same. Those cancel. J squared, -1. I'm subtracting that. So this now becomes A squared plus B squared. And in terms of an A and a B, orthogonally related, the hypotenuse is just the square root of the real part squared plus the imaginary part squared. So that now A squared plus B squared is really just the length of A plus JB squared, or the magnitude of A plus JB quantity squared. And that now is the same as I sub s magnitude squared. That's where that comes from. So if somebody says I have a complex number times its complex conjugate, you can say, oh, that simplifies a lot. Now I just have to find the magnitude of that complex number and square it. Is that clear? That's where that I star simplified down to just having the magnitude of I squared. That, I hope that aside firms that up for everyone. Now somebody might ask, now that we're finished with the aside, what if somebody said, what's the power factor of the load? Now you could just start writing down some formulas and figuring out what you need to find. The power of our load you could write as the magnitude of our voltage. So the voltage, depending on how you're writing it, if it was a phasor quantity, you really just need the magnitude of that voltage phasor times the magnitude of the current of our load, which was I sub s, cosine of theta sub L, where this piece is what? That's the apparent power of the load. Here's the apparent power. And this is the power factor of our load. So that now you could actually compute the power factor of the load as the ratio of the real power of the load divided by the apparent power of the load, which is really the same as the cosine of theta sub L. So it really depends on what you have available to you maybe when you're trying to answer the question, the power factor of the load. You could solve it many different ways. If we go back now and look at what we found, we converted the load power into an apparent power at an angle. Oh, we have the angle of that complex power. We could take the cosine of that and get the same answer as dividing P sub L divided by the apparent power. So we could do this many different ways. This we found to be 377.52, or we computed it. This was 473.36, or we could just say, well, that's the cosine of 37.1. Do you see you can have all different ways of calculating that power factor depending on what information you have or that you see at the moment, or that you feel comfortable using. If we now take the cosine of 37.1 degrees, what's the cosine of 45 degrees? You might want to kind of remember that. That's the 0.707, right? Now the cosine of 37 should be what relative to 0.707? Bigger or smaller? Should be bigger, right? So we should expect a number. If you're plugging these things into your calculator and you see a number and you're writing it down, you're going, does that kind of make sense? Oh yeah, it does, because I know the cosine of 45 is 0.7. Here, if we did the cosine of 37 and get this equal to basically 0.798, are we finished with finding the power factor? You guess. We don't want to guess in this class. You can guess today, but not on the exam. Don't guess on the exam. You want to be prepared. You don't want to be guessing. Well, anything, if you don't have an answer, it's better to guess than just leave it blank, right? Gamble. Yeah, we're all into gambling, right? But you want to minimize the risk of that gamble by studying for the exam. But now the power factor actually needs more than just the numerical value. Yeah, really. What else do we need? We need to know, is it leading or lagging? Was that power inductive or capacitive in nature? And which was this? It was inductive. So that means what? Just go back to Eli. You're not going to forget him until you retire. So Eli, I is lagging the E, so this is a lagging power factor. And you found that because you were remembering that it was an inductive load. But Q was positive, wasn't it? In this power written in its rectangular form, the complex power. Well, this is so fun, I don't want to stop. So let's find the complex power of the line. How do we find that? How did I tell you to find the complex power of the load? VI star. So let's do it some other way. So let's do it another way. Just to show you that there are many different ways to approach these problems. Another way would be what? Well, the complex power of the line would be the total power supplied by the source minus the complex power that's being consumed or absorbed by the load. This now we could find as, and did we say hat, minus S sub L. Because really we have the supplied equaling the absorbed. And now we're just solving for S sub lowercase l, where the supplied power was S sub S bar hat equaling S sub lower l plus S sub capital L. And now we just do the algebra to solve for S sub little l. Or this now, since we have these already, there's no reason to start playing with V times I again. Why find those? Now we have the supplied, which was 387.2 plus J290.4 minus 377.52 plus J285.56. And hopefully that's consistent with what we had, so that now we do the algebra and we have 9.68 real power of the transmission line plus J 4.84 volt amperes. Can we look at this circuit from any other angle? What if we look at the apparent? Did we calculate the apparent power of the source? What is that going to be? One formula for that. In terms of the variables that we have available to us. The apparent power of the source. What's the power company concerned about? The power you're apparently requiring, right? So they are going to charge you based on the apparent power that you're asking them to supply. And that's now in terms of the variables that we've played with, that's the magnitude of V sub s times the magnitude of I sub s, which in this case was 220 times 2.2, or 484 volt amperes. And one more question for this circuit. What's the power factor at the source, or of the source? What's the power factor of the source? What would you like it to be? 0? Ooh, boy, you're going to be in hot water with your boss if your power factor is 0. Then what are you doing? You're not doing any useful work. You're just pulling and giving back because your power factor is 0, right? You want it to be 1. So you want the angle to be 0. That's probably what you were thinking. So you want the angle to be 0, but it isn't. Was our source at a 0 angle? Did we have any length of Q? We did, didn't we? And do you remember the angle? Wasn't it this 36.87 or 0.8? And what was the sine, SIGN, of that angle? That gets thrown out when you find the cosine, but you really need to know it in order to complete your answer for power factor of the source. This was positive, wasn't it? Which means, what's the second piece of the power factor answer? Is it leading or lagging? Lagging with positive Q or positive angle. This is now 0.8 lagging. Pardon? So why is the power factor lagging? What does that correspond to? If we have a lagging power factor, what does that represent in terms of the type of circuit that we have? It's inductive, isn't it? That's Eli. You could have just said, Eli, right. Because Eli has what? The I lagging the voltage. But on the exam, don't say Eli. No. You could write it down, but then you could say lagging. So here it's 0.8 lagging. That's what that means. Any other questions on the quiz? Yes?
So is it generally if you have a positive power factor, or I don't know if it's specific to this problem, but it's the power factor is positive, and that's
So now what is our power factor? The question is concerning the sign of our power factor. What if I gave you a capacitive load, and I now had a load that was minus 36.87 for its angle? I take the cosine of negative 36.87, and what's it going to be? Positive 0.8. That's why it's important that you add that little label of lagging or leading, because you lose it when you take the cosine of that angle. Our angles are hopefully going to be living between plus and minus 90 degrees. And so now we'll have cosine of negative 45 is 0.707. Cosine of positive 45 is 0.707. You need to give me more information than just 0.707. Do you see why? Now that angle gets lost when we take the cosine, since the cosine's an even function. And the information that you deliver or include to your answer, is it lagging or leading? The power factor. It's lagging if it's inductive. It's leading if it's capacitive. Question.
What is the issue with just having complex power? Like what does happen to the transmission line if I just pull in and then give it away?
So now what happens if I think what you're asking is, what if I just have reactive component and no real part? Then what's happening at your factory? No useful work. You're simply energizing whatever you have, let's say your inductors in your plant, and then you're throwing it back to the power company. And they're going, boy, he wants current. Power factor 0, but I'm going to charge you. Yeah, you're going to lose a lot of power. You do have current going back and forth on the transmission line, and you're going to probably have some resistance in that transmission line. We don't yet have ideal, non-resistive transmission lines, do we? That's why these transmission lines might be big. You're trying to minimize the loss, the resistive losses going back and forth, but there's going to be some resistive losses. The power company says, he's asking for quite a bit. And you're over here going, what's happening in here? Nothing. But you're still getting something. You know, you're asking something of the power company. And nothing's happening. At your end. The power company, yeah, lots happening. So you probably want to get a little something for your money, unless you like to just burn money. And your boss, she may not want you just burning money. Why are we paying for power we're not using? Okay, I'll buy a capacitor bank and... Well, actually, you want your machines to be more efficient than that, to just be inductors, right? You want it to be turning something. Anyway, let's move on. Question. Why do we use the conjugate of the current? Anybody remember that? So last time we derived the expression, and it falls out, but essentially, if you look at... How do I want to say this? If you can look at it many different ways, and maybe we'll do it differently, but if you just had something like this, how would you describe the power in that circuit? VI, right? Or you could say this is VI, but now you have R times I is V times I, so that now you have RI squared, and everything's real there. It's a real number. Up here, we are actually more interested in the situation where this Z is complex. And now we have a V, and we have an I. But really, we're kind of wanting to keep this same structure. And one way to view that is to say, oh, if I now look at V I star, what's going to happen? Well, now when I use V is ZI times I star, I now have Z times the magnitude of I squared, which is consistent with RI squared. But you can go back and look at how we derived it last time. This is just kind of a really quick justification, but really the power depends on the impedance, whether you have inductive or capacitive. But if we didn't conjugate that current, what would have happened down here? We would have had a bad answer, wouldn't we? We would have had S is equal to ZI times I. And then what do you have? You have Z times I squared. Is this red quantity the same as the black quantity? No. So it's not consistent if you didn't conjugate that current to begin with. That's one way to maybe convince yourself, why do I have VI star? This is not what you want. But I trying to just emphasize, why do we want VI star? It's because we really want to be worrying about Z times the magnitude of I squared. Let's now move on to another example. Where we have a two-terminal element. And suppose in this element, here is our voltage across that, and here is our current, I of t, and suppose we are asked to find the complex power for this element when V of t is now 100 cosine omega t plus 15 degrees volts, and I of t is now 4 sine omega t minus 15 degrees amps. All right, now what's going on? What do you have to keep track of? Now you need to just calm down and look at what you have and think through what you need to do. The very first thing that you might want to do is, wait a minute, I can't just be multiplying cosines and sines. They all have to have the same, either cosine or sine, and in this class we're going to agree put everything in the cosine form. So our very first step is to say, let me at least start by converting I into a cosine expression. So now what will that be? 4 cosine. If I'm converting omega, the frequency stays the same. Now what do I do? And you can convince yourself, if you go back and look at Euler, you can make sure that that sine of x is equal to cosine x minus 90. Knowing that, now we can say, oh, this is now a phase of minus 105. Now what do we do? Now we're in pretty good shape. We can now try to find the power. We want the complex power. Do we have formulas for the different components of our power? And now you can say, is our load, is that element resistive? Is that element resistive just by looking at V and I?
Yeah, a lot.
Is it purely resistive? What? What are you asking? Can you, by inspection, tell me if this is a purely resistive two-terminal element? Okay, that was a yes-no answer. So I asked, can you tell me? Now I want you to answer, is it a purely resistive?
No.
Why? Okay, the current and the voltage are not aligned. The peaks are not aligned, or as are the valleys. There's a phase shift difference between the voltage and the current. So there's going to be some reactive power in this. So you can just look at that and say, whoa, I have a P and a Q. If I now start doing the P, what's the formula that I'm going to use? Now, do I have, what units am I going to be using? Pardon? VARs? Well, I'll be using VARs at some point, but not right now with P. P is in watts, right? P is watts, Q is VARs, but now in this formula for P, what do I right now have available to me? What is this? This is actually V max, isn't it? And this is I max. So you could either convert those to RMS before we start using the P formula, or we could just use the P formula using maximum amplitudes. Let's just do it that way, just to make your life miserable. We now say that this is 1/2 V max, I max. Is that it? There we go. We have to account for this phase shift between the voltage and the current. Theta sub V minus theta sub I. And there's another reason why we need to conjugate the current. There is really the angle of the impedance, isn't it? Which is theta V minus theta I. That's Z's angle. The Z of that particular element's impedance. Yes?
So I understand that, like, given the RMS of V and I, like, we wouldn't have to do the 1/2, but for like, let's say on a quiz or a test, are you gonna exclusively make them all VMs or VRMS?
The question was, are you going to give us the answers of the exam? No. So, I don't know. So you need to be prepared. The question was, are you going to give us RMS? Are you going to give us maximum values? I don't know. So be prepared. That's why I'm giving you this particular example, so that you can see that, oh, well, I might have to do this for maximums. I might say, oh, let's assume that this V is an RMS V. Then its magnitude would have actually been an RMS magnitude. Do you see how I could really mess it up? But just be prepared. Here, if I don't say RMS, you're going to have to assume that those are maximum amplitudes. So if it's not labeled RMS, just assume, and I would label it. I would say, oh, he's assuming that's VM. Oh, he's assuming that's IM. I would label it. Now we have this. We now have this as 1/2. Vmax was something, 100. Imax was 4. Cosine of 15 degrees minus a minus 105. So that now we have 1/2 100 4 cosine of 120 degrees. This is 200. Cosine of 120, I said we'd be dealing with angles between plus and minus 90, so I'm not quite so honest here. But this is now cosine of 120. You would expect that to be negative. And that's a negative 1/2, so that we end up with minus 100 watts. By the labeling, the way that we had labeled that two-terminal element, that was the absorbed power. So in fact, that two-terminal element is doing what? It's supplying 100 watts to whatever it's connected to. And we can determine that because it's minus some quantity absorbed. What about Q?
Minus 100, not minus 200.
It's minus 100 because we
Cosine, right.
cosine there is actually minus 1/2. We okay there with P? Let's now do our Q. Q is again in maximum amplitudes. V max, I max, sine of theta sub V minus theta sub I. This is now 200. That hasn't changed, but this is now the sine of 120 degrees. That's now this square root of 3 over 2. Sine of 120 is positive. So this is now 173.2. That's what you were wanting. That's the VARs. There we go. Here we go. And what is this? Absorbed or supplied? Absorbed. And then we have to decide truly what is it based on the sign of our result. So now we have this reactive component actually being absorbed. Meaning, let me try to write this down. Therefore, the element, the two-terminal element that we drew as a box, is delivering, oh, there's delivering. Let me see if I use it consistent with mastering. Is delivering 100 watts to the rest of the system. Through the two terminals that we had identified, and absorbing what you could say are magnetizing VARs at its terminals. And it's magnetizing because it's inductive. So that now that two-terminal device has a complex power S sub E of minus 100 plus J 173.2 VARs absorbed. Because you really don't want to say absorbed, delivered, supplied. You just want to use one and then label the powers with a plus or minus, depending on what they are. Questions on that example? Pardon? You guys tell him. You can't hear me. Was it inductive or? What was our Q? Why is everybody going? My power, I lost my power. Was it real or reactive? Now I'm shouting and I shouldn't be because I'm still recording. But what you were hearing, you kind of lost me. It was imaginary, wasn't it? There was some Q somewhere. And what I wanted to do was talk about complex power expressions. So There's no one in this room after we leave, so we're not leaving. It's a long weekend, so you might as well enjoy this class. What? You have lab? What's a lab? So, what I will do probably after class is derive some power expressions and show you, hopefully, how this impedance might enter into if I wanted to keep currents or if I wanted to use voltages. Meaning I have Z, I magnitude squared, or I could have, so let me just show you what I want to end up with. We've already seen this one, where Z is I magnitude squared. The other one is going to be in terms of voltage, if you have that available to you. It's now V magnitude squared divided by the conjugate of your impedance. I'll try to show that in the notes after you go to lab or wherever you go. Okay? Some of you might be enjoying these phasers that have bars over the top. You might be going to a bar. Never mind. So we'll be picking up here on Tuesday.